Exponential equations. How do we solve exponential equations? Well, exponential equations are equations that have a variable in the exponent that we're trying to solve for, like maybe 128 equals 2 to the x power. We're going to be dealing with some higher power of 2 that's going to give us 128, which begs the question, if atheists don't believe in higher powers, can they solve exponential equations? Okay, maybe not that type of higher power. Most exponential equations we cannot solve with our current experience. We're going to need a new toolkit that we'll pick up in Algebra 2. But there are a few that we can solve if we can rewrite the problem so that both sides of the equations have and use the same base. In other words, the 128 in that first example can be rewritten as 2 to the 7th power. 2 times 2 times 2 times 2 times 2 times 2 times 2 is 128. So now my original problem can become 2 to the 7th power equals x. And if both bases are 2, you could imagine then both exponents must be the same. So the exponent of 7 must equal the exponent of x. And we've solved this exponential equation. But before we get to really manipulating these exponents, I want to review some rules of exponents. Remember, if we have a squared cubed, that means a squared is we've got 2a's. And cubed means it happens 3 times, which means there's a total of 6 a's being multiplied together. When we have an exponent raised to an exponent, we will multiply those exponents together. And in this lesson, we're going to do a lot of distributing as we multiply those exponents together. Another important property is if we were dividing exponents, we've got a to the 5th. That means there's 5 a's in the numerator. And a squared, there's 2 a's in the denominator. Well, 2 of them are going to divide out, and we're just left with a cubed. And so we see with division, with the 5 and 2, we could have just subtracted those exponents, and we would have ended up with the a cubed. So division, we subtract exponents. And kind of a corollary of that is if we flip the fraction upside down, a squared over a to the 5th, well, if we use that subtraction property, 2 minus 5 would give us a to the negative 3. Well, that's weird. What the heck is a negative 3 exponent mean? Well, let's look at what happens with the fraction when we reduce. A squared is a times a. Over a cubed would be 5a's. Well, 2 of them divide out, which means we just have a 1 left in the numerator. That numerator doesn't disappear. Over a cubed. Which means both of these must be the same. 1 over a cubed is equal to a to the negative 3. In other words, negative exponents, like negative 3, mean we've got a fraction with the positive exponent in the denominator. So negative exponents make that reciprocal fraction, and then the exponent becomes positive. We're going to use that quite a bit today. So 3 important properties that we've reviewed. Those are going to help us solve exponential equations like these 6 examples here. Remember, our general strategy with exponential equations is going to be to get the same base, because then the exponents must also be the same. In this first example, 5 to the x minus 6 equals 5 to the 4x plus 2. We've already got the same base of 5. So that means these exponents must be the same. X minus 6 must equal 4x plus 2. Now we're ready to solve this simpler equation. We've solved equations like this before. We'll subtract the x off of both sides. Negative 6 equals 4 minus 1 is 3x plus 2. Subtract 2 from both sides. 3x equals 6 minus 2 is negative 8. And divide by 3. And x, I'm running out of space, so I'm going to come over here. Hopefully we won't run out of space completely. Negative 8/3 is equal to my x. So when x is negative 8/3, our equation is a true statement. Now, usually we're going to have to do a little bit of work, though, to get that same base on both sides. The second example here, 3 to the x equals 81. You can see they don't have the same base. However, we can write the 81 so it matches the base of 3. I can divide 81 by 3 4 times. 81 is 3 to the 4th power. So 3 to the x equals 3 to the 4th power. Now we've got that same base that we wanted. Now we've got that base of 3. So the exponents must be equal. X must equal 4. Sometimes we have to do that same work on both sides of the equation. This second example, 16 to the x equals 8. We can't rewrite 16 as 8 to some power. That doesn't work. However, they're both divisible by 2 over and over again. 16 is actually 2 to the 4th power. Still have an x on it. And 8 is 2 to the 3rd power. Now, what I want to notice is we've got a double exponent. Remember, we have a property that says double exponents mean we multiply them. So we'll say 2 to the 4 times x equals 2 to the 3rd power. And now we've got that same base that we want, so our exponents must be equal. 4x equals 3. Divide both sides by 4, and x is equal to 3/4. So 16 to the 3/4 power equals 8. How about this one? 25 to the x plus 3 equals 125 to the 3x minus 1. We can't say 25 to some power equals 125. That doesn't work. But we might notice, hey, those look like they're divisible by 5 several times. So we'll check, and sure enough, 25 is 5 squared to the x plus 3. And 125 is 5 to the 3rd power, to the 3x minus 1. Again, we've got the double exponents, so we have to multiply them. Just be careful, we don't just multiply the 2 by the x, we have to multiply by the entire exponent. The entire exponent needs to be multiplied by 3. So we have 5 to the 2x plus 6 as we distribute, equals 5 to the 9x minus 3. That exponent has to go to the entire thing. Same base. We can set the exponents equal. 2x plus 6 equals 9x minus 3. Get the x's to one side by subtracting 2x. We've done this a lot before by now. 6 equals 7x minus 3. Add 3 to both sides. 9 equals 7x. Divide by 7. And we get the fraction 9/7 is equal to our x. If we can get the same base on both sides, the exponents must be equal. But what if there's a fraction? Remember, fractions come from negative exponents. That was that last exponent property we saw. So 1/10 can be rewritten as 10 to the negative 1. And I probably don't need that parentheses, because that's all that's going on there. 1/10 is 10 to the negative 1. A negative exponent means the fraction is flipped. We're trying to get the same base. Can we write 100 with a base of 10? Yes, we can. 100 is 10 squared. So now we've got a double exponent. We know that gets multiplied. So 10 to the negative 1 equals 10 to the 2x. And now we've got the same base on both sides of 10, so the exponents must be equal. -1 equals 2x. And that solves really fast by dividing by 2. X is equal to a -1/2. Last example is going to combine several of these concepts together. We have a fraction, so we know we're going to deal with a negative exponent. 25 we know is 5 squared, but it has to be negative, so that way it accounts for the negative exponent creating the fraction, all to the x power. 625 can also be written as 5 to some power. That's actually 5 to the 4th power with an x plus 3 on it. Multiply exponents. Remember that 4 has to distribute onto both parts, so we've got 5 to the -2x equals 5 to the 4x plus 4 times 3 is 12. And now we've got that same base of 5, so our exponents must be equal. -2x is equal to 4x plus 12. Let's get the x's to one side by subtracting 4x from both sides. So -6x equals 12. Divide both sides by -6. And x equals -2. So that's the gist behind solving exponential equations, at least as far as we know right now. Get that same base on both sides, and then we can set the exponents equal. One little catch, though, is the exponent part must be alone. We have to solve for the exponent part first. So if I've got a problem like this, here is my exponent part. I have to get that part alone first, which means I have to get rid of the -17 and the 3. And if I think about this, if this was 3a minus 17 equals 7, we know how to solve that. We would add the 17 and divide 3. Then we'd have the a alone. Same exact strategy here. We want to get that exponent stuff alone, so we'll start by adding 17 to both sides of the equation, always balancing on the equals. Then we've got 3 times 1 over 128 to the x equals 24. Get rid of that 3 by dividing both sides by 3. And 1 over 128 to the x equals 8. And now we're ready to write both sides with the same base. Let's switch over to green. 128 can be rewritten with a base of 2. That's 2 to the 7th power. But because it's a fraction, it needs to be a -7 raised to the x equals 8 can also be written as 2 to the 3rd power. And now we know we can multiply those together. I'm running out of space, so we're going to come over here. We've got 2 to the -7x equals 2 to the 3rd power. And now we've got the same base, so we can set those exponents equal. -7x equals 3. Divide both sides by the -7. And x is the fraction -3/7. And we've solved this equation. So first, make sure, if needed, you solve for the exponential part first. Then get that same base. And now you know how to solve basic exponential equations. Good luck on the homework, and let your instructor know if you have any questions.